Hello everyone. We will continue our discussion on analysis of traffic for bituminous pavement design. So the references for this session is Pavement Analysis and Design by Huang and Principles of Pavement Design by Yoder and Witzak, and I also will be discussing the code provisions. My acknowledgement to the Google sources from where some photographs are taken. So the outline of this session will be, you will see how the traffic is analyzed in terms of equivalent single axle loads by three different approaches. The first one is a vehicle damage factor method, the second is an average truck factor method, and the third is a load spectra factor method. A quick recap of what we have discussed in the last lecture. We actually discussed that you want to convert all the given axles or the load types or the vehicle types to some standard axle. Okay, the standard axle that we have considered is a single axle dual wheel having a total load of 80 kilonewton or 18 kilopounds. Okay, so this was the standard axle that you have considered, and you wanted to convert all the given axles to this standard axle. So for the single axle dual wheels of different wheel loads, what we have seen is that this conversion factor can be determined based on the failure criteria. So we have considered the two failure criteria which is mostly used for pavement design. One is fatigue cracking and second one is rutting, and accordingly we have determined what is the EALF factor for each of the load, axle load, which is given as sigma Ti by sigma Ts raised to 4. So the fourth power law is considered, and sigma T represents the tensile stress on the flexible or the bituminous layer. I represents the axle load under consideration, and S is the standard axle load. Now this what we have observed is that if you use the fatigue cracking criteria or the rutting criteria, it more or less gives a similar results, as you see that in the case of fatigue cracking, you can determine the equivalent axle load factor as epsilon Ti by epsilon Ts raised to 4, where epsilon T represents the tensile strain at the bottom of the bituminous layer. Whereas if you are considering the rutting criteria, your EALF, that is equivalent axle load factor, can be determined as epsilon Ci by epsilon Cs raised to 4, where epsilon C represents the compressive stress on top of the subgrade layer. Now this can be approximately equal to the load, the given axle load divided by the load of the standard axle, which is 18 if it is in kilopounds, or 80 kilonewton if we are expressing in SI units, okay, raised to 4. So this is what we have found out, or this is the conversion factor or the EALF factor for single axle dual wheels. Now if you have a tandem axle or a tridem axle loads, you can't directly apply find the critical strains as epsilon T, epsilon C, etc. under a dual, a tandem or a tridem axle load and use this expression to find the EALF. That is not directly possible. Why? Because a tandem axle, one tandem axle cannot be considered as equal to one single axle dual wheel, or it cannot be considered as equivalent to two single axle dual wheels also. So it will be somewhere in between. So that is why you need to adopt a damage analysis concept in the case of tandem axle and tridem axle to determine the EALF, rather than directly using the epsilon T and epsilon C under those axle loads. Okay, so what you have seen is that you have to determine the damage ratio as given here, as we have already discussed, and then the damage ratio due to the tandem or the tridem axle divided by the damage ratio due to the single axle can give you the EALF for the tandem or tridem axle. And then what we have seen is that in IRC 37/2018, the equivalency factors are given in terms of the power law, the fourth power law, as we see that if it is a single axle with single wheel on either side, you can take the standard axle load as 65 kilonewton and the given axle load in kilonewton divided by 64 raised to 4 is the equivalency factor. whereas if it is a single axle dual wheel, it is axle load divided by 80 raised to 4. And in the case of tandem and tridem axles, based on this damage analysis, it is observed that an equivalent load of LS is equal to, or the standard load of LS is equal to 148 kilonewton can be adopted to find the equivalency factor to convert the tandem wheel load to a single axle dual wheel load. Okay. So similarly, a tridem axle, the equivalent load or the standard load is given as 224 kilonewton, so that the equivalency factor can be determined as axle load in kilonewton, the axle load in question divided by 224 raised to 4. So these are the equivalent axle load factors given in IRC 37 to convert a single axle single wheel, a single axle dual wheel, a tandem axle and a tridem axle to an equivalent single axle dual wheel assembly like this. Okay. Now coming to the Asphalt Institute method, based on the ASHO, the American Associate of State Highway Officials road test, mostly the failures were considered to be from rutting, and from this ASHO test results, they have given the equivalent axle load factors. Mostly it will be on this fourth power law itself. So we see that for the different axle loads here, so this is a table representing the equivalency factors. So for different axle loads, you see from 1000 pounds to all with the way up to 80,000 pounds, you have the equivalent axle load factors are given if it is a single axle or if it's a tandem axle or a tridem axle. The equivalency factors are given here. We can have a quick look. You see that if it is 18 kilopounds or 18,000 pounds, you see that the equivalency factor for a single axle is 1. Okay. Whereas if you consider 36 kilopounds, for example, suppose you have a tandem axle which is coming with double the load, which is 36 kilopounds, you see that the tandem axle equivalency factor is not 2 but it is 1.38. Okay. So from this table you can directly take the equivalent axle load factors if you are designing as per the Asphalt Institute method. So this is what we have discussed so far in the last lectures, how or what is that equivalent factor that has to be used to convert the given axle load to a standard axle load. Okay. Now let's see how to arrive at the equivalent single axle load repetitions from the total traffic. See, what you see here is a traffic which comprises of different types of trucks with different axle configurations and having different weights. Okay. Now what you have to convert it to, you have to convert it into a number of repetitions of 80 kilonewton single axle dual wheels. So as you see here, you call it as the equivalent single axle load, so you call it as ESALs. So this conversion, how to do and how to get it, and by applying the equivalency factors that we have already discussed is what we are going to discuss in this lecture. Okay. Now, as I said, there are three approaches. One is a vehicle damage factor method. The second is a truck factor method or an average truck factor method. And the third one is a load spectra factor method. Okay. We'll see each one of this one by one. So the first one is by the vehicle factor method. So the vehicle damage factor method. Okay. So the vehicle damage factor, or you generally call it as VDF, is that multiplier to convert the number of commercial vehicles of different standard axle loads and axle configurations into the number of repetitions of the standard axle load of 80 kilonewton, single axle dual wheel of 80 kilonewton or 18 kilopascal. Now this is a method that is adopted in IRC 37 2018. We will see what is this VDF. Okay. See, this is the traffic load or the traffic in the stream. As I have already shown, you have different classes of trucks, you have different trucks with different loading as well as different axle configurations. You have to find that one multiplier which can convert it into number of repetitions of the standard axle. Okay. So how to get this one multiplier or this vehicle damage factor is that you will find out what is the equivalent axle loads corresponding to all the axle loads of all the vehicles in the stream, then sum it up divided by the total number of vehicles considered will give you one vehicle damage factor for the entire stream together. Okay. Now let's see how to calculate it. Let me explain the procedure. Mostly I will be explaining with respect to the IRC method, okay, IRC 37 2018 approach. So first of all, what you need is the total traffic spectra. The traffic load data has to be collected, and then this traffic load data will be divided based on the axle type, and a frequency distribution table can be prepared. So for each axle type, we will see how many number of axles are falling in each load group. Okay. Now what you do is that you divide it into a number of intervals or class intervals. Essentially, now how you divide it into the class interval can affect the VDF value. So IRC 37 suggests that you group or make bin sizes of 10 kilonewton for the single axle loads. If it is a tandem axle load, you can make a bin size of say 20 kilonewton, and for tridem axle loads, you can make a bin size of 30 kilonewton. Essentially, because the loads will be larger, so you can have a range of 30 kilonewton as a bin size, I mean the class interval. Okay. Now you consider, you divide the entire axle load into each these frequency prepare it in the frequency table, and the mid value of each of the bin of the frequency distribution will be considered. Say for example, in the case of the 10 to 20 kilonewton axle load bin, 15 kilonewton will be taken as the average load in that category, and each of this, see this, now the equivalent axle loads will be found out by multiplying the frequency that is falling in each one of this bin size with their corresponding EALF values. Okay. So see, what you see is that you 15 kilonewton, if 15 kilonewton is the mid value of that bin of that particular group, you find out what is its EALF using these expressions as given in the equivalency factor expressions given in IRC 37, which is, for example, if it is a single axle dual wheel, the given axle, which is 15 kilonewton, divided by 80 raised to 4. So that will give you the EALF factor. Now once you get the EALF factor, you can multiply the EALF values corresponding to the number of axles in that group. Suppose there are, like, say 25 axles in this group, so you get the EALF for this particular axle load group and multiply it with 25, that is a frequency, that will give you the conversion to equivalent single axle loads for that bin or for that axle group. Okay. So for a particular axle type, you have different axle load groups. You add all the equivalent axle load values together to get the total ESAL corresponding to that axle group. Okay. Say for example, if you have different axle types such as named as single axle, single wheel SS, single axle dual wheel, tandem axle, tridem axle, etc. So from the traffic, you have divided all the single axles from all the vehicles together, put it in different class groups, and then you have determined the equivalent axle loads for that. Similarly, you have found out the equivalent axle loads for all the single axle dual wheels in that vehicle group. Similarly, the tandem axle and the tridem axle, and all these equivalent axle load values can be added together to get the total EAL value. Okay. So as you see here, the total equivalent axle loads is equal to, now suppose you have considered in the whole spectrum, you have considered say 1000 vehicles. So divided by the total number of vehicles will give you this vehicle damage factor for that axle, the loads spectra that you have collected, or that for that traffic, this forms the vehicle damage factor. Okay. How to consider the traffic as per IRC 37, let us discuss what is the input that goes in here. So what I have discussed is only the vehicle damage factor. Now this vehicle damage factor has to be used to get the total ESALs. So let's see of the traffic, of the actual traffic. So let's see how that is done. So the input that you require is the initial traffic. Okay. Now what you are going to find out is what is the cumulative standard axle loads for a given road for a given design period, for which you are going to design the payment structure. So first you need the initial traffic. So normally the two-way traffic on the road after construction in terms of the number of commercial vehicles CVPD or the commercial vehicles per day is to be considered. Now this, when I say commercial vehicles, the weight more than the vehicles or the truck vehicles or the heavy commercial vehicles having laden weight more than 3 tons will be considered for payment design. And in order to get this commercial vehicles per day, you have to take the average of a 7-day 24-hour count. Okay, so this number of commercial vehicles per day should be the count at the beginning of the functioning of the new structure or the new payment. Okay, then you need the average traffic growth rates of either the growth rate for the entire vehicle classes or different growth rate for the different vehicle groups, and then the design life in number of years and the spectrum of axle loads. As I said, you need the axle load information, so that is the spectrum of axle loads, and also other factors for the estimation of a lateral distribution of traffic over the carriageway. Okay, so these are the input data that are required. We will discuss each one of them one by one. The first one is the traffic growth rate. Now this value has to be extended over the design period so as to get the cumulative traffic, right? So you need what is the rate at which this traffic grows. Now this traffic growth rate is expressed as a percentage of increase or percentage increase from year to year. Now how does this traffic grow? The first thing is that there can be a normal traffic growth over the years due to increased number of usage of motor vehicles. Now, there could be other possible reasons of increase in the traffic growth. One is the attracted or diverted traffic due to the improvement of an existing pavement or due to the construction of a new pavement. It may attract more traffic towards that. So, that can increase the traffic or that can contribute to the traffic growth. And another is generated traffic. Because since a new facility or a payment is created, there could be more traffic that is generated because more vehicle trips may happen. And another one is that development traffic, because there could be changes in the land use or development of the region because of this new facility, which can attract more traffic. So all these reasons can contribute to the traffic growth, and while estimating the growth rate, you have to consider all these factors. Okay. And of course, the traffic growth over the previous years can be considered to predict the traffic growth in the coming years. Okay, now, and one more aspect is that this traffic actually varies on a daily basis as well as on a monthly basis. So, the data that you actually use is an estimate of the average traffic over the life of the payment. Okay. Now, let us say that we know what is the traffic, initial traffic on day 1 or day 0, say for example EL0. Now if you want to find out what is the traffic on a future date EAN, then you can find it by projecting it by this expression, which is EAL0 into 1 plus R raised to n into 365. Now EAL0 here is the initial daily traffic. Okay, on the day the traffic is open on the road, or you can consider that it is at the end of the 0th year, or that is at the starting of the first year. So that is the traffic on the 0th period. Okay, so if you have that 1 plus R raised to n, that is the conversion, or that is how you can project it to a future year, which is at after n years. Okay, and R is the growth rate. Now why 365? Because this data is given for per day. So multiplying with 365 will give you the traffic in a future year, in a year. Okay, so yearly traffic you will get. Now let us see what is the rate at which, or let us assume this is the traffic growth rate. So the daily EAL or equivalent axle loads. What I have mentioned here is the equivalent axle loads. Likewise, it can be the number of vehicles or number of trucks and so on. Okay. So let us say that the daily equivalent axle loads increases in this fashion. So this is the trend that is given, or the growth trend over the years, in n years. Now for the design, you need to find out, suppose you are going to design the payment for n years, you want to find what is the traffic that is accumulated over this design period. Okay, so that you can get as the area under this load progression, the traffic progression curve. So how to get this area under the curve? we can first of all find out what is the total traffic for this n years from this graph from. So what you have to do is that you have to integrate the value from the 0th year to the nth year to find the total traffic. Okay, so as you can see, it is written here in expression 4. The total traffic from the 0th year to the nth traffic is given by an integral 0 to n of this expression, okay, of this expression, which is used to predict the traffic at any future date. Okay, so it becomes EAL 0 into 365 into integral 0 to n of 1 plus r raised to n dn. Now this integration, on integrating, you get that it is 1 plus r raised to n minus 1 by log to the base c of 1 plus r. Now the growth rates are mostly less than say 10%. So when mod r is less than 1, your log e to the log of 1 plus r to the base e is close to r. So you can replace this with r, so that the total equivalent axle loads over the n years is EAL. The total EAL, which is given by EAL 0 into 365 into 1 plus r raised to n minus 1 by r. So this factor here, this 1 plus r raised to n minus 1 by r can be termed as G, which is the growth factor. Okay, so this is how you estimate the traffic growth, and you find out what is the total traffic at a future date, or what is the total traffic over the design period, which has to be considered for design. Okay. Now the traffic growth rate, as I already mentioned, it can be estimated based on the past trends of traffic growth, and also what is the demand that is expected to the specific development and land use change, etc. This traffic growth rate need not be same for all classes of vehicles. Like for one truck type, it may be different from another one. So you can estimate the traffic growth rates for different categories of commercial vehicles. And if this data is not available, IRC suggests that the annual growth rate of commercial vehicles, if it is less than 5% also, you have to take a minimum annual growth rate of 5%. This is what IRC 37 suggests. Okay. And regarding the design period N, IRC 37 says that you can choose the number of years of for which the road is designed based on the class of the road as well as the way in which this construction is planned. So essentially, if the category of the road is national highways, state highways or urban roads, you can choose a design period of say 20 years. Whereas for other categories of roads like minor roads or district roads and so on, you can choose up to 15 years for the design of bituminous pavements. And in the case of high density corridors with the total equivalent standard axle loads, which is more than 300 million standard axles, that is MSA, and for expressways and all, you go for a larger design period of 30 years. Now, you may not always do this the construction at the beginning itself for the total design period. You can go for a stage construction also. That is possible in the case of flexible pavements or bituminous pavements. So this, if it is a stage construction, you can choose a lesser design period, lesser number of years for the design as per the how the stage construction is planned. Now, in order to get this axle data, you have to conduct an axle load survey. Now, the axle load survey has to be conducted on a similar section or a similar stretch of road like the one which we are going to construct, or on a similar category of road. You can do the axle load survey to get to investigate what will be the type of axle load spectra that will come in the new construction, okay, or the new pavement that you are planning. So, in order to conduct this axle load survey, you can have a static method or a weigh in motion method. So, in the static method, what you do is that the load of the vehicles will be measured when the vehicle is stationary, okay, for which you have the stationary weigh bridges, or you can use portable type weigh bridges or weigh pads. As you can see here, see this is a stationary weigh bridge. So, what is done is that the vehicle will be allowed to stand on top of that weigh bridge, and then you can calculate or you can measure what is the total weight of the vehicle. Now this type of weighing is essentially done for measuring the overloading of heavy loaded trucks and not for empty trucks. This method is used. Okay. Now, in the road, if you want to get the actual axle load spectra, you normally go for this portable type weigh bridges or weigh pads, so that this can be positioned near to the highway where where you want to conduct this axle load survey, and you can ask the vehicles to move over on top of these weigh pads or weigh bridges, and the weights of these vehicles or the axles can be noted. Now, in the case of what you see here is a portable weigh pad. So, in the case of a portable weigh pads like this, you can measure the axle loads separately. Suppose it is a tandem axle, you can first ask the driver to move this vehicle on the first wheel of the tandem axle on top of this weigh pad. You can measure that, and then you can move the next wheel and measure the load. So, for each axle, you can measure the vehicle loads separately. Now, in this picture, you see that there are two weigh pads are used so that you can measure the load on the whole axle together, but sometimes this also may not be happening. What you can use is that you can use a single weigh pad, with the assumption is that on the either side of the axle, both the wheels will be carrying equal amount of, or it's equally distributed on both sides. So, you will just measure the weight of one wheel on one side of the axle, so that multiplying it with 2 will give you the total weight on the axle. Okay. So, this is the portable weigh pads, or you can also have portable weigh bridges, which is it's like slightly bigger in size. You can again ask but again here the total load of the vehicle will be measured. So, essentially for the axle load surveys that you do in highways, you go for this portable weigh pads. Now, the other method is the weigh in motion technique. So, this is essentially an automatic axle load data collection system. The major disadvantage with the static method is that you have to ask each one of the vehicle to pass on top of the weigh bridge, and it has to be stopped there for considerable time till still you know the weight and so on. So, this may cause some disruption to the moving traffic. So, this can be avoided if it's in the case of a weigh in motion technique. So, here the truck volume, the axle configuration, what is the axle spacing, the speed of the vehicle, the axle and the gross weights, everything can be collected automatically without hindering the regular traffic flow. So, what is done is that certain sensors will be installed in the roadway or under the bridge over which the vehicle are allowed to pass at their operational speeds itself, and then that will the sensors will capture this data. But compared to the static method, the errors associated with weigh in motion methods are considered to be a little larger. That's what the literature says. And there can be various arrangements of sensors on the road to collect this information. To see, this is some of the configurations of weigh in motion systems as per Liu et al. In 2002. You see that this is a traffic flow direction, and there is a bending plate or a pressure cell scale is used here, and there is an axle sensor also is there to sense the axles, and there is an inductive loop. So, or there are like piezoelectric sensors which are arranged on two or more piezoelectric sensors are arranged. So, these are the different ways in which or configurations you can have to have the weigh in motion measurement of axle loads. Okay. Now, as per IRC 37/2018, it suggests that you have to conduct the axle load survey for 24 hours in each direction of traffic. Okay. Now, it may not be possible to stop all the vehicles in a particular stream and measure the traffic loads. So, a sampling has to be done, and it is suggested that this minimum sample size that has to be chosen in order to conduct this axle load survey is given as at least 20% of the commercial traffic. Not the 20% of the total traffic, it's the 20% of the commercial traffic is to be surveyed. If the number of commercial vehicles per day is less than 3,000, and if the traffic is between 3000 to 6000, at least 15% of the commercial vehicle traffic is to be surveyed, subject to a minimum of 600 CVPD. And if the truck traffic is more than 6000 CVPD, at least 10% of the vehicles are to be surveyed. So these are some of the pictures wherein this is like a bigger kind of pads that are used for the axle load data collection. So whereas this is a small portable type of weigh pads being used for finding the axle loads. So this is how the sampling is done, and then the axle load data will be collected. Now, using this axle load data, we will determine what is the vehicle damage factor, and that vehicle damage factor will be used to determine the equivalent standard axle loads for the traffic, that is for the design traffic. Okay. But IRC 37 also suggests that if it's in the case of small projects, or if it is not possible to collect such extensive axle load data, then certain indicative VDF values that are given in the code can be used, which is given in table 4.2 of IRC 37. If the initial two-way traffic volume in terms of commercial vehicles per day is 0 to 150, you can use a VDF for a vehicle damage factor of 1.7 for plain or rolling terrain. So IRC suggests different VDF values for plain and rolling terrain and the hilly terrains. So in the hilly terrains, you can go for a VDF value of 0.6. Similarly, for say if the CVPD is more than 1500, you can use a vehicle damage factor of 5 or 2.8 respectively. So this is what IRC suggests if you don't have provision for conducting an axle load survey. This is done only for small scale projects. Okay. Now, the next factor that is to be considered for determining the equivalent standard axle loads is the lateral distribution of traffic. Now, you can have different class of or the different number of lanes, and you will have traffic in both directions. Like say if it's a north-south, you can be a north-south road, you will have the northbound traffic as well as the southbound traffic. Now, based on the number of lanes, the point or the number of vehicles or the percentage of traffic that will stress or strain a particular point in the traffic will vary. Okay. So based on that, you need not design for the 100% of the traffic on the road, but you can have a certain lateral distribution factor. So we will see what is the lateral distribution factor that can be used based on the number of lanes and the type of whether it is a divided lane or an undivided one. So if you have a single lane road, then in that case you have to design based on the total number of commercial vehicles in both the direction, or the direction distribution factor has to be taken as 1. So let us assume that this is a single lane road, you have vehicles moving in both directions, to the north as well as south direction, then the chances that every vehicle will load a particular point in the pavement is 100%. Okay. So you have to use the entire traffic for the design, for consideration of the design. So that is why the direction distribution factor is taken as 1, and the traffic has to be the total traffic in both the directions. Suppose you have a slightly larger width of road, say you call it as an intermediate lane road of 5.5 meter, you can choose 75% of the total commercial traffic on both directions can be used, since the width is slightly more. Okay. Now, if you have a two-lane two-way road, there is lane, but it is not a divided one. If you have two lanes, you use 50% of the total commercial vehicles in both directions. So you can have this, there is a lane, no division in the one direction and the other direction. You take the total and take the 50% of that. Now, if it is a 4-lane single carriageway, so the single carriageway, it is not divided, you have 4 lanes, you can go for 40% of the total commercial vehicles in both directions. Now, suppose it is a dual 2-lane carriageway, see there is a separator or there is a median in between, then in that case you take 75% of the number of commercial vehicles in each direction. So what you have to do is, you measure the traffic in both directions, you see which is the heaviest traffic, and you can take 75% of the commercial vehicle in that particular direction. Okay. Where if it is a dual 3-lane carriageway, it is separated 3-lane carriageway, then you can go for 60% of the number of commercial vehicles in each direction. Now, if it is a dual 4-lane carriageway, the lane distribution factor can be 45% of the number of commercial vehicles with each direction. Okay. So, this is how the lane distribution factor is chosen in IRC 37. Okay. Now, let's see, based on using all these input parameters, how the total design traffic is considered. Okay. You call it as end design or the equivalent single axle loads ESALs. Okay. The expression is 365 into 1 plus r raised to n minus 1 by r into A into D into L into VDF, which is the vehicle damage factor. Okay. So, this is a screenshot of the front page of IRC 37 2018. Now, what is end design? So, end design is the cumulative number of standard axles that is to be catered during the design for a period of n years. Suppose n is the small n is the number of years for which you are going to design the pavement. Now, A is the initial traffic volume or the commercial traffic volume per day in the year of completion of construction or in the date in which you are opening the pavement for traffic. Okay. Now, suppose this data is not available. This you might have taken the you might have taken the traffic volume count some years prior to that. Then in that case, first of all, you have to find what is the traffic volume, initial traffic volume A before projecting it for n years. So, how do you do that? So, A is given as P into 1 plus R raised to X, the same concept that we have already discussed, just projecting it to a future date where R is the growth rate. So, P is the traffic that is measured on any particular or the last count that you have taken into 1 plus R raised to X, where R is the growth rate and X is the number of years between this count is taken and the year of completion of the pavement construction or the year when the pavement is open to traffic. So, you will get A, that is the initial traffic on that pavement, the new pavement, and then for projecting it to a future date after n years, you get this growth factor. You have this growth factor which is 1 plus r raised to n minus 1 by r. Now, multiplying it with 365 will convert it into the yearly traffic. Now, we have these three parameters D, L and VDF. So, D is the directional distribution factor or the lateral distribution factor that we have already discussed, and L is the lane distribution factor. Suppose we have considered the traffic in both direction, whether it has to be taken as 50% or 100%. So, that is the lane distribution factor, and VDF is the vehicle damage factor that we have already discussed. Okay. Using the VDF, you are essentially multiplying the VDF with the traffic or the initial traffic, so that everything is converted into the equivalent standard axle loads. Okay, and that is then projected to the future of n years. So, this is how the total end design or the design traffic is computed in the case of IRC 37 2018.